Okay, we've seen some really interesting facts about the rational numbers. For one thing, the rational numbers are countable, which means that there are the same number of rational numbers as there are positive integers. That's surprising because between any two positive integers are infinitely many rational numbers, and yet somehow those two sets are the same size, they have the same cardinality. But going along with that idea that between any two integers are infinitely many rational numbers is this idea that the rational numbers are what we call dense on the number line, which means that they are very, very tightly interspersed throughout the number line. Between any two numbers, there are infinitely many rational numbers, in fact, no matter how close together those numbers are. Okay, so somehow the rational numbers are countable and dense. Let's add to that a third idea, which is that the set of rational numbers has what we call measure zero. What that means is that the width of the rational numbers, if you could push all of them together, like put one hand at positive infinity, one hand at negative infinity, and kind of squeeze all the rational numbers so that they're all next to each other, they wouldn't have any positive width. So even though they're dense, they don't account for much of the number line, and that kind of goes along with the fact that they're countable. Okay, so to calculate the measure, the width of the set of rational numbers, we're going to use this bijection that we get from the natural numbers to the rational numbers to enumerate our set of rational numbers. So since we have a bijection from natural numbers to rational numbers, we can use that bijection to write down the rational numbers as a list, where the first rational number, which I'm calling r sub 1 here, is wherever our bijection maps the natural number 1, r sub 2 is f of 2, r sub 3 is f of 3, etc., etc. Now to calculate the width, what I'm going to do is pick any size width I like. I'm going to call that epsilon. Let epsilon be greater than 0, and ultimately what we'll show is that the width of the set of rational numbers is comparable to epsilon. So then if mentally you imagine epsilon to be really, really small, and then even smaller and even smaller, what you get to conclude is that the rational numbers don't really have a positive width. So let's say that this is r sub 1, this is r sub 2, here's r sub 3. What I'm going to do around r sub 1 is draw an interval that looks like r1 minus epsilon over a fourth, epsilon over 4, to r1 plus epsilon over 4. So this is an open interval with r1 sitting in the middle. And the radius of this open interval is epsilon over 4. Okay, now what I'm going to do is go to the second rational number r sub 2, and my notion of second here comes from that bijection. And I'm going to draw an open neighborhood around it, but its radius is going to be half of the radius I just used. So we're going to go to r2 minus epsilon over 8, all the way to the right to r2 plus epsilon over 8. Here the radius is epsilon over 8. Then we can go over to the third rational number, r3, and do the same thing where again the radius is going to be half of the previous radius. So here our radius around r3 would be epsilon over 2 to the 4th power. Okay, around every rational number we're going to draw such an open interval, so every rational number is going to get covered by one of these open intervals, in fact by several, but at least by one, the one centered around it. Okay, now what we can do is try to add up the widths of all of those open intervals and show that even though we've got our open interval associated to each rational number, the total width of all of these open intervals is really, really small. Now we can say that our family of rational numbers is sitting inside of the union of all of those open intervals, since each rational number gets to be the center of one of those open intervals. Now let's add up the lengths of all of those open intervals. Well, it's just going to be the right endpoint of each one minus the left endpoint. Okay, so that looks like Rn plus epsilon divided by 2 to the n plus 1 minus Rn minus epsilon divided by 2 to the n plus 1. The Rn's cancel out. So the length That doesn't depend on where we centered our interval. Now after some simplification, notice epsilon here is just a number, so we can factor it out in front of the sum, and what we're left with is epsilon times a geometric sum. So from here to here I'm using geometric sum formula. So the total width of all of these open intervals that we designed is epsilon. Epsilon was a positive number, but it was arbitrarily small. If I wanted to make my widths even smaller, I would just pick a smaller epsilon. You can pick epsilon as small as you like. Therefore, we say the set of rational numbers has measure 0. How I like to imagine this is that the rational numbers don't have a positive width as far as the set goes, and yet if you look at the number line, it definitely has a width to it. So when you look at the number line and you see this line going from the left side to the right side, that line is mostly irrational numbers. We've already mentioned this when we said that irrational numbers are uncountable and rational numbers are countable. But now what we can say is rational numbers are what gives the number line its width. Any interval has a positive width. Every interval has that positive width because it contains irrational numbers, not because it contains rational numbers. Again, if you could squash all of the rational numbers together, they would essentially squash up into a single point. They just don't have positive width as a set. Let's look at a function called Thomai's function. What this function does is it takes the value 1 if x is 0 or 1. So that's like down here, this is the point 0, 0, and over on the right, this is the point 1, 0. Between 0 and 1, what it does is if x is rational and written in reduced form, say for example x equals 1/2 but not x equals 2/4, then it takes the denominator and replaces the numerator with 1. So x equals 2/3 would get mapped to 1/3, x equals 1/2 would get mapped to 1/2. And you can see that's actually the biggest value because 1/2 is greater than 1/3, 1/4, 1/5, 1/6, every other possible denominator that we could have. So this tall point up here is the point 1/2, 1/2, and this is 1/3, and then over here this is where 2/3 got sent, and then we have 1/4, but we don't have 2/4 because that would be 1/2, but then we do have 3/4. Then we have 1/5, 2/5 get sent to 1/5, 3/5 get sent to 1/5, 4/5 get sent to 1/5, etc. So you can see how this function behaves on all the rationals is it takes p over q in reduced form and sends it to 1 over q. And then if x is irrational, it stays at 0. We're not going to prove this fact, but this function is discontinuous at every rational number, but it's continuous at every irrational number. You can work out why that would be true if you think in terms of decimal expansions. If you want to prove that this number is continuous at every irrational number, we'll take an irrational number. It has some infinite non-repeating decimal expansion. If you define some radius around that number to be very, very small, then every number inside that radius would have the same decimal expansion up to a certain number of places, say 100 places. Any number inside that radius which is irrational is going to get sent to 0, which is fine. We're comparing it to an irrational number where the output is 0. Any rational number, though, with that many places in its decimal expansion would be sent to 1 over a very large number, which would be close to 0. So it's hard to imagine, but this function is continuous at all of the irrational numbers and discontinuous on all of the rational numbers. The question is this function integrable? We have infinitely many points of discontinuity, and our points of discontinuity are not clustered around one single point like they may have been in previous examples. Instead, our points of discontinuity are pretty evenly spread out across this interval, so I can't just enclose infinitely many, the bulk of the points of discontinuity into one small neighborhood. Yet it turns out this function is integrable. Here's the theorem. If the set of discontinuities has measure 0, that's a concept you've seen before, then your function is integrable. We're just going to state this, we're not going to prove it, but how would you prove it? Well, if your set of discontinuities has measure 0, that means that you can enclose all of the discontinuities into a bunch of neighborhoods whose total width is as narrow as you like. And that's the key idea, is that the total width of the neighborhoods containing the points of discontinuity can be made very, very narrow so that it doesn't contribute a lot to your upper and lower sums. So I just want to mention this result without going into further detail, that even if you have an infinite number of discontinuities and you can't even say that they're all clustered up together, you may still be able to have an integrable function.